We're going to take a brief pause from the action in section 2.3 and go back and take a look at something in section 2.2. It's problem number 30. And basically what they want you to do is experiment with different viewing windows to try and select the best one. And my goal in giving this to you is to try and give you a little guidance or a few thoughts about adjusting your windows so that you can get a good looking graph, something that would be helpful to get information from. Now the way this works is we're going to start by putting in the function that they give us here, y equals x squared minus x minus 20. So x squared minus x minus 20. And then we're going to experiment with different viewing windows. So what they're giving you here is x min, x max, then y min, and y max. So for the first one here, I'm going to set that up from -2 to 2 on the x-axis, and from -5 to 5 on the y-axis. Once you get those adjustments set, then press the graph key and see what we get. Pretty uninteresting graph, huh? Or maybe our viewing window wasn't good enough because we're not seeing anything. Our graph is positioned a little different. Now there's a default setting that a lot of your calculators will start out with fresh from the package, -10 to 10, -10 to 10. You can set your window manually that way. Kind of a faster way to get to there would be to zoom standard. So zoom 6, at least on my calculator, it's zoom 6. And that'll set up from -10 to 10. At least we see something this time. But what important feature is missing out of this graph? The vertex, yeah. So obviously we're not going low enough to see the vertex. So, and then, some of this stuff to the side, well, maybe we don't need that stuff to the side, but definitely we need to go lower. So let's take a look at part C here. Actually, maybe we should do D first. Because all we have to do to get D is adjust our window on the y-axis between -100 and 100. So let's do part D first. I'll keep the x min and x max the same. This time we're going to go between -100 and 100. Let's do something else here that's not really covered by the problem itself, and that is let's adjust y scale. Because if I leave y scale equal to 1, it's going to try and put 200 tick marks up and down the y-axis, and it's just going to look crazy. It's not going to help us out at all. So let's pick a bigger number, something that goes into 100 evenly, maybe 25. So on the y-axis, the tick marks are going to represent units of 25. At least now we see the vertex, right? Is that a better looking graph than what we had before? Yeah, that one's getting better. Now, I guess my complaint here, though, would be that you're wasting a lot of space. I mean, that bottom, third of the graph is just empty space. So what you might do is try and shore that up. Try and not go down quite so far. Now, remember, these tick marks represent units of 25. So, a good lower limit on this would be, say, -25. And I don't need to go all the way up. So let's go back and do part C now. There they have a window between -7 and 7. We can leave y or x scale equal to 1 because we don't have too many tick marks there. On the y-axis, let's go between -25 and 20 for y max. I don't want to leave y scale as 25 anymore. Let me choose 5, a smaller y scale. And now I've got a really good graph. It fills up the picture, it fills up the screen pretty well. I can see the important feature, which is the vertex, and I'm pretty happy with that one. So, did that help a little bit in terms of what you would want to do? I mean, some of this you're just going to have to experiment with. The zoom fit key works pretty nice. In fact, let's hit zoom fit here. It's not going to adjust the graph much, but it will adjust it a little bit. And what it'll do is it'll make it just barely fit our graph. It's going to use up all the available space. So zoom and then 0. Sometimes I actually like a little space underneath it or above it, depending on the graph. But we're getting a pretty good graph this way as well. You can look back and see what it adjusted. It adjusted Y max to be 36, and Y min is a little bit further down than it was. Okay, so let's go back to section 2.3. We're going to stick with the graphing calculator, and I'm not sure I'd make this a test problem, but I am going to take the time to show you how to do problem number 28. If this did appear on a test, I'd probably make it an extra credit problem. This is 2.3. So we're back in section 2.3. And they want us to use our graphing calculator, which is this little symbol here, to solve these equations graphically. So I want to try and figure out where 5x squared minus x cubed equals negative x squared plus 3x plus 4. So where is that going to be true? Well, there's a couple different approaches. Here's my idea. Let's graph y equals the left-hand side versus y equals the right-hand side and see where those two graphs cross each other. So that's our goal. So we're going to enter in two functions. So hit the y equals key and do 5x squared minus x cubed, and that's one graph. And then our other graph is going to be negative x squared plus 3x, plus 3x plus 4. So I've got both of those. Now I don't know exactly where to see the graph until I play around with this. Now I'll give you a choice. Do you want to play around with it together, or do you want me to just tell you, all right, just use these values? Doesn't matter to me. Just tell us. Just tell me. All right. So if we graph this between, let's go between negative 3, negative 3 and 6 on the x-axis, and negative 15 and 20 on the y-axis, we should get a pretty good graph of both of these functions. So the first one's your cubic function. The second one is your parabola, the squared function. And notice that opens down, as you could probably predict from the fact that we have a negative x squared. How many places are there where these two functions are actually equal? 3. Now, there's a couple ways you can find them. Depends if you want to find them exactly or roughly. If you want to find them roughly, you can hit the trace key. Trace key is located along the bottom row of your window. Hit the trace key and then just kind of move around and get close to where they look like they intersect. So there's one there. Or I can type in a number. It's kind of like a guess. It looks like this one intersects at about negative 1/2, so negative 0.5. If I just type that in, it'll put my cursor over there. I can try and get a little bit closer. But if I want an exact value, then again, my calculator can help me. So let's try and figure out exactly where these two cross. Hit the second key, then the calc key. Calc is right above the trace key here. So second and then trace. And it gives you this menu. Does there look like there's something on this menu that would be helpful? Intersect. Yeah, we want to find the intersection. So it's going to ask you for a point on the first curve near the point of intersection. I'm already pretty close there, so I'll just press the enter key. And then it moves you to the second curve and asks you the same thing. So I'll do the same thing again. You press enter one more time, and it'll give you the x and y coordinates of your intersection, so about negative 0.584. So nice. So you can find out exactly where that intersection is. And I can repeat that for this one and this one as well. Once you have these, you can answer the question below that, which is, where is one function bigger than the other? But once you have those x values, it should be clear that this function's bigger here, and then the red function, the parabola is bigger in this interval, etc. But the key thing is being able to find these points of intersection. So, can I answer some more questions on finding those points? We're good on that? Are you able to keep up with what we're doing on the calculator? Okay. We are going to continue to work with the calculator a lot. I think it's kind of silly to deny that we're in the 21st century and do things completely by hand. You can, but it will require some math that we just don't have yet. Let's kind of give you a little bit of a softball topic for just a minute. Increasing and decreasing functions. So, hopefully this is something that in mathematics is named in an appropriate way that makes sense to you. So for an increasing function, like this first one, as you move from left to right, the graph is getting bigger in the y direction. It's moving north. So that's an increasing function. Decreasing function is doing the opposite. As you move from left to right, the graph is decreasing. That is, it's moving down along the y-axis, or its y-coordinates are getting smaller. Oops. There we go. The only thing that's tricky about increasing and decreasing functions is your answers. When I ask you where a function is increasing and decreasing, you need to give me x coordinates, an interval of numbers, between x1 and x2, for instance. Those have to be in interval notation. Let's start with problem number 32. Okay, so we want to figure out where this function is increasing and where it's decreasing. Let's start here in this first interval, say to the left of 0. What's the function doing there? Decreasing. Now I drew that line along the x-axis because your interval, your answer has to be in intervals along the x-axis. So that green line covers the points that we need to discuss. It's between -2 and 0. That's where it's decreasing. Then what happens to the function? Good. So it's decreasing from -2 to 0. And use parentheses around that. It's increasing. Where? Where does it increase? Not for very long, right? Yeah, just 0 to 1. So it's increasing from 0 to 1. Then it starts decreasing. What interval is it decreasing on? Good, 1 to 3. And again, just use parentheses for answers for increasing and decreasing. So overall, your answer should look like this. Decreasing from -2 to 0, union 1 to 3, and increasing from 0 to 1. It's handy, if you know what these graphs look like, when you're determining increasing and decreasing. But you might not always know what they look like. For instance, problem number 42. Y equals 4 minus x to the 2/3. We're going to do the same thing there. Y equals 4 minus x to the 2/3. Determine where it's increasing and decreasing. But like I said, you kind of really need to know what the graph looks like first. So what are we going to do? How are we going to figure out what that graph looks like? Yeah, graph it on the calculator, right? That's what you have these high-tech toys for. So depending on your calculator, you're going to have to be a little bit careful entering that function. I notice a lot of you have 83s out there. Those are about as old as you are. So a little bit long in the tooth, but they're still going to work fine for what we need here. But when you do 4 minus x raised to the 2/3, for those of you with an 83 or without an up-to-date operating system, you're going to have to enter that as y equals 4 minus x raised to the parenthesis 2 divided by 3. It's just the way that one's going to have to work. If you've got a more up-to-date operating system and it puts something in the exponent like this, I need just to do 2 divided by 3, and I'm good. Now, I need a window here. So I'm going to give myself kind of a big catch-all. I'm going to go between -8 and 8. But I don't know what to expect on the y-axis. If I don't know what to expect on the y-axis, what's my cheat? What's my shortcut? Zoom fit. So zoom 0, and that'll just set the y values for me, and I don't really have to worry about things. So you get this unique cusp kind of behavior here. And the function, I can assure you, continues going down to the left and down to the right from there. But with this graph, see if you can't answer increasing and decreasing now. If you want, we can make our window a little bit bigger, -10 to 10, just so you can see that the graph continues its downward behavior. There you go. But try and determine where it's increasing and where it's decreasing. Well, all the way to the left. So where would that begin? Well, negative infinity. Good. So it begins increasing at negative infinity. Negative infinity to where? 0. And then starts decreasing. 0 to what? Positive infinity. Thank you. Let's combine increasing and decreasing with another notion that I want to look at in section 2.3, and that is min and max. So let's try problem number 44. So a couple things that we're going to want to know is where it's increasing and decreasing. And I'm going to let you work on that. Now you're going to kind of have to estimate it based on the graph. I'm not looking for, perfection here, but you should be able to give me a decent guess as to where these things are increasing and decreasing. So Let me give you a moment or two to think about those. Increasing and decreasing. Yes. Yeah, you can expect that the lines keep going. So, in fact, let's do this. Let's put a little arrow here, a little arrow there. Yeah, they keep going. Good question. Very relevant, too. It certainly changed the answer a lot. Decrease from -2 to 0. -2 to 0. Maybe she was looking at increasing because it's increasing in the next 0 to 2. She must have it's increasing there. So you're not crazy.
I thought I would.
All right. Okay, so there's a couple points here that are kind of key and critical. This one here at -2, one at 0, and another one at 2. So in terms of increasing, the function is increasing until it gets to this x value, until it gets to -2, at which point it starts decreasing. So increasing here, decreasing, and then increasing again, and then decreasing. Overall, increasing from -infinity to -2, and from 0 to 2. And then decreasing on the intervening intervals. So I'll write that down in a second. There is one other thing that it asks you in this problem, and that is to find all the local maximum and local minimums of the functions. So a local max is a point that's bigger than anything near it. For instance, this point right here. It's bigger than anything near it. So at x equal 2, you'll have a local max. What kind of a point do you think I'll have here at x equals 0? A local minimum. And then at negative 2, again, we've got another local max. And technically, that's actually a global max. The function doesn't get any bigger than that, assuming that it continues down in both directions here. So this would be a global max. I'm not going to make you worry about that distinction. If I ask you for local min, local max, I'm looking for these kinds of points where a function either has a peak or a little valley. Okay, so write things down. We had increasing from negative infinity to negative 2, union 0 to 2, and then decreasing from negative 2 to 0, union 2 to infinity. The local max would be at negative 2 and 2. And the local min at x equals 0. Okay, not so bad. Let's try problem number 56. Again, trying to get some more information out of our graphs. This one is the graph of the acceleration of the ground in an earthquake. Does anyone know what these kind of things are called, these measurements? Yeah, seismic waves. Yeah, and it's measured on eventually it's measured on a logarithmic scale called the Richter scale. So I don't think that's exactly what's graphed here, but what's graphed here is good enough. It shows the 1994 Northridge earthquake in LA. So a few questions that it asks here. At what time did the earthquake first make noticeable movements in the earth? How long did you have to wait before you could tell there was an earthquake, at least on this graph? Yeah, 5 seconds. So at what time did the earthquake seem to end? Yeah, about 30. Where's the maximum intensity of the earthquake? Where did it max out? Yeah, about 17 works for me too. So be curious to figure out exactly what the value is on the Richter scale there, but that's okay. So a couple quick values there. One last one from this section. Problem number 60. I think we're going to see this one again too, this graph. So the population of a small industrial town from 1950 to 2000 says determine the intervals on which P is increasing and P is decreasing. So where is P increasing? What interval? This is your population. Where is it increasing? 0 to 25. So if that's 1950 is 0, then till 1975, then what happens? Yeah, it's decrease. So that actually answers another of our questions is what was the maximum population and in what year was it attained? Well, the year attained was 1975. What was that maximum population? 50,000. Good. This is find the net change in population from 1970 to 1990. So they actually have a couple points on the graph for us already. Can you tell just by looking at the graph without taking out your calculator what's the net change in population? 0. These are both on the same horizontal line, so there's no difference in the y coordinates. The difference in the y coordinates would be your net change. The net change here is 0. They told us. 1970, 1990. So if this is 1950, right here, 1960, 1970. That would be that one. Oops. A blackout. Sorry about that. Lamp. There. There we go. So if this is 1950, this is 1960, that'd be 1970, 80, and then 90. So those 2 points, 70 and 90. For homework, try 7 through 21. 27/29, might be an extra credit question on an exam. 31 through 49, and 55 and 57.